In this video, we will discuss some code forces techniques that do not have an explicit name but are very useful to solve problems related to binary string. We'll start out with a simple problem that asks you to find out the number of substrings in a binary string where the number of zeros and ones are equal. So if you have this binary string, like let's say 1 0 0 1 1 0 1 1, then you can see that this is one example of a substring where the number of zeros is equal to 2 and the number of ones is also equal to 2. So you have to count how many such substrings satisfy this property. So in this video, I'll give you a series of techniques that you can also use in other problems. So let's start out with the first technique, which says that in certain problems that involve binary string, if it is helpful for you, then you can replace all the zeros with -1, and that might give you new perspective to solve the problem. So if you have this binary string, we can replace all the zeros with -1 like so. So let's say we have 1 and then -1, -1 and 1. So you can see that the original string was 1 0 0 1. So nothing has changed, right? Because only the notation of 0 is now switched to -1. But once you do this transformation, you can see that this problem is now asking you to find the substrings with equal number of -1s and 1s. But what does an equal number of -1 and 1 implies? It means that the sub-array sum should be equal to 0. So sub-array sum is 0. Now, this itself is not an easy problem to solve. So, we'll have to see whether this simplification is actually useful for us or not. So, even though this might be a difficult problem or maybe not, but at least for the binary strings case where when you are only dealing with ones and -1, this is a very easy problem to solve. And when we actually solve this problem of figuring out how many subarrays have sum equal to 0, we can actually solve the general version as well. Like given a general array G, you can actually find out the number of subarrays with sum equal to 0. So now I'll introduce you to the second technique. So the second technique says that in problems like this that involve a subarray sum, and remember that subarray deals with multiple elements at once, right, from L to R. So any subarray that deals with sum can be converted to just two elements by inspecting just two elements using something known as a prefix sum, right? So the technique one was replacing zeros with -1, and technique 2 that I'm introducing right now is called prefix sum of a subarray. Sorry, it's called sum of a subarray is equal to difference of two elements in prefix sum array. So this is a very simple fact, but this is very powerful because let's take this example. So it says that if you want to compute the sum of the subarray from here to here, suppose this is index X and this is index Y, then you compute your prefix sum. That is, the prefix sum will be equal to this element, then this element, then sum of all these elements will be the third element of the prefix sum array, then sum of all of these elements will be the fourth element of the prefix array, and so on. So you can see that if you want to compute this sum, right, this small length, this is nothing but this big length, sum of all elements till index Y, minus this small length, sum of all elements till index X minus 1. So that sum is nothing but prefix of Y minus prefix of x minus 1. So this is the second technique, that sum of subarray is equal to the difference of two elements in a prefix sum array. Now, why is this transformation helpful for us? Because previously we were thinking of a lot of elements at the same time, but now we only have to focus on two elements on the prefix sum array. Then, of course, this naturally leads us to the third technique, which is sum is equal to 0 implies prefix of y minus prefix of x minus 1 is equal to 0. Therefore, prefix of y is equal to prefix of x minus 1. So you can already see that if you want to compute, if you want to find out the sum of, if you want to check whether the sum of this subarray is equal to 0 or not very quickly, then you can just pre-compute the prefix sum array, and then you can check whether the index, whether the element at this position and this position, are they equal or not. If they are equal, then definitely this subarray will have sum 0. So this is the third technique that we discussed, right? So yeah. So first technique was replacing all the zeros with -1. Second technique was converting to a prefix sum array is usually helpful in analyzing these problems. And the third technique was, if you want to find out the sum of all elements equal to 0, if you want to check that condition, then you only have to check whether the two elements of a prefix sum array are equal or not. So we can now reduce the original string based problem to an isolated problem that just says that given an array given an array A, how many pairs of identical elements are there? As simple as that. How many identical pairs are there? So how do you find that out? So suppose the values are A, you have B, C, A, C, B, A, and then D. So to find that out, you can see that if you want a subarray with identical endpoints, basically the subarray with sum 0, then you have to, if you are selecting one endpoint as A, then the other point also has to be A, right? So you just count the occurrences of all the A, which is what? 1, 2, 3, 4, 5. So A has 5 positions. B has how many positions? 1, 2, 3. And then C has how many? 1, 2, 2. And then D has 1. So now there are 5 locations at which A is present. So if you select any of these 2 locations as your corresponding pair, that subarray will have sum 0, right? So the contribution from element A is 5C2. Similarly, for element B is 3C2. For element C is 2C2. And for element D, it's nothing because it's just one element, right? You have to form a pair with identical thing to get 0, right? So this is the fourth technique. The fourth technique basically says that when you want to find out all the subarrays with sum 0, instead of trying to iterate over all the subarrays, you now iterate over all the values, right? Iterate over all the values and check how much this particular value will contribute, right? So this is kind of a contribution technique. And then we also talked about some combinatorics over here, which is very simple. All you have to do is you have to select 2 elements out of x possible elements. So the number of choices is xe2. Now don't come at me in the comment section that you missed some corner case where the subarray is of length 1 or it is the entire prefix. So that's not the point of this video. Yes, I might have missed an off by 1 error, but that's fine, because what I want you to learn from this video is the general idea that how would you solve this problem. Now of course when you are submitting this problem, then you can handle all the corner cases, which is what if there is no left endpoint and you are taking this entire subarray, right? So for example, what I mean by that is, suppose this subarray from element 0 to element at this position, this subarray itself has sum 0, then its prefix sum will also be 0, right? Then it actually does not need a left endpoint to, it does not need a left endpoint, right? To convert from 0 minus 0 is equal to 0, because this is already 0. So that part is very trivial. You can handle by just adding an if somewhere, or basically taking an extra contribution. That is fine. So now we have solved the problem in O of n, right? You can see that we started out with a difficult problem, which is across all substrings, which is O of n square. You were expected to find number of equal zeros and ones, right? Number of substrings with equal zeros and ones. And we did that by first converting the zeros to minus ones, then converting it to prefix sum, then getting the notation that the subarray sum is equal to difference of two elements in the prefix sum, then getting the idea that difference of two elements is equal to 0 means identical element, and then applying some combinatorics to figure out that the contribution of an element x is nothing but its frequency C2, right? So far so good, and a lot of you might already be aware of these techniques, right? But now in this video, I want to discuss some difficult problems on as well that build upon this technique, right? And that problem is called substrings of substrings with equals zeros and ones. Now now let me show you what I mean by that. So suppose you have this 1 0 1 0, and let's say you have 1 0. Then how many substrings? So in the first problem, I asked you to simply find out how many substrings are there and tell me which substrings have identical number of zeros and ones. Now what I want you to do is, for each substring that there is in this subarray, for each substring, solve the original problem. Solve the original problem. So you can see that this is one possible substring, and inside this substring, you have to find out how many zeros and ones are there. How many substrings are there in which the number of zeros and ones are identical, right? So for example, inside this substring, this is one possible answer. Then this is one possible answer. Then this entire substring is also one possible answer, right? And then this is also an answer, right? Like 1 1 0, and then okay, so this entire thing, but I hope you get the idea, right? So you have to count for each of the substring how many substrings are there with an equal number of zeros and 1. Now let's see how we can utilize that same idea of prefix sum, plus 1 minus 1, contribution technique, etc. to solve this problem. So now I'll introduce you to the next technique, which says that instead of trying to iterate over all the substrings, right? Let's look at let's change our perspective. Okay, so let's change our perspective and you flip the narrative. So right now the narrative is asking you to, for each substring, compute all the valid substrings, right? So now you flip the narrative and you say that if you have a valid substring, right, let's say that begins at position x and ends at position y, if you have a valid substring, and by that I mean uh, this subarray sum is equal to 0, right? And suppose this valid substring, okay, let me start a new page. What I was saying is, suppose you have this original string, and in this original string, this substring, assume that this is a good substring, that is the number of ones and zeros in this substring is equal, right? And this is index 1, this is index x, this is index y, this is index n, right? Now, instead of worrying about all the subarrays, you try to do some contribution technique on this subarray. That is, you ask the question, in how many subarrays will this particular subarray contribute? So to contribute, this subarray has to be embedded in a big subarray, and for that embedding to be possible, the bigger subarray should start from the left hand side and end at the right hand side. So how many choices are there for the bigger subarray to start? So you can see that the bigger subarray can start from any of these endpoints, right? So there are total of x choices on the left hand side, and there are total of n minus y plus 1 choices on the right hand side. So if you take their product, right? So x into n minus x into n minus y plus 1 is the number of subarrays in which this subarray will also be present. It means that in all of those subarrays, this element will contribute, this subarray will contribute 1, right? Because we want to find out the sum, right? So the contribution of this element is x into n minus y plus 1, given that the prefix of x minus 1 and prefix of y matches. So basically you will add an indicator variable over here, just like you do in probability and expected value problems. So there is an indicator variable that says that prefix of y, prefix sum of y is equals prefix sum of x minus 1. So now keep paying attention, like we have already introduced a new technique, right? The new technique is that instead of thinking about subarrays, you figure out a good subset and then you see which subarrays will include it. And this is a very powerful, and I believe this is one of the most important contribution technique that I have been seeing in recent code forces around. That is, you take something and you figure out in which bigger sets will this element be a part of. And how many are there? It is simply x into n minus y plus 1 into this indicator variable. Now, how do you compute this sum effectively? Right? Because you still have to iterate over all x and y, right? To get this answer, right? And that will be O of n square. So now I want to introduce you to another technique which says that when you are dealing with such contribution technique problems, and if it involves a subarray, then what you do is you fix the right endpoint or fix any endpoint and then count the contribution again. So you do fix a right endpoint. Right now, suppose if you fix this right endpoint y, right, y is fixed, then x can vary, and once x varies, the contribution also varies. But let's see how much x varies. Right now, at this point, the contribution is nothing but x into n minus y plus 1. So this part will always be constant because you have fixed y, right? So you remove this y on the left hand, you take this on the left hand side, and then you see that the contribution simply becomes x into the indicator variable, right? You take this out over here. So this means that for each y, you have to find out the sum of indices into the indicator variable of all such x, right? Now finding out the indicator variable, whether this will be 1 or 0, that is easy. All you have to do is you have to maintain map, right, of prefix sums, right? So let's start with a new page. So just to recap, we are here and here. This is position x, this is position y, this is position 1, this is position n, and we are trying to find the contribution that this element y will provide. So f of y will be nothing but n minus y plus 1 into summation of x into x into the indicator variable, and this indicator variable is nothing but prefix sum of y is equal to prefix sum of x minus 1. Now you can start iterating from left to right and keep all the prefix sum in a map, right? So let's say you have seen prefix sum 2, 5, 9, 2 again. So you keep all of them in a map along with their count. Okay. When you reach the element y, right, what you are interested in is how many times have you seen prefix sum. Suppose the prefix sum at y is p star. So you are interested in how many times on the left hand side have you seen p star. So suppose you have seen p star at this location, this location, this location, and this location. So when you were writing down this contribution formula, you must have written this same n minus y plus 1 into this x star, this x star, this x star, and this x star, right? And you must have summed them up. So you can see that if you sum all of these value over here, you can get this n minus y plus 1 factor out. And then what you are essentially interested in is the sum of indices of all of these, right? So now all you have to maintain is for each prefix sum, you have to maintain sum of x, and where x is the index of the occurrence of this prefix sum. And then when you reach this element y, you just multiply the sum, right? Because this sum will look like, so if this is I1, this is I2, this is I3, and this is I4. So the P star in your map will contain I1 plus I2 plus I3 plus I4, right? So all you have to do is find the prefix sum from your map and then multiply it with n minus y plus 1, because we know that this indicator variable will always be 1 because their prefix is matching, and for the remaining part their indicator variable will be 0, right? So this way you can find out the contribution of each element just by iterating from left to right, and then you have your answer in O of n. Or like if you are assuming that you are maintaining the map, then you have your answer in O of n log n. But then again, another technique to notice that in binary strings problem, what is the maximum sum? It is 2 into n. Sorry, the maximum sum is n and the minimum sum is minus n, right? So if you just maintain an array of size 2n, then you can even get rid of this log factor in this map based problem, but not a big deal at all. Okay, so you're not solving a late code problems that you have to worry about all of these minute space complexity details. That's fine. But yeah, I hope you got the idea that how we were able to solve a very complex problem, which is computing the substrings of substrings with equal zeros and ones. And just to recap what all we have learned so far, that is, the first technique is, it is somehow always beneficial if the problem demands it, that replace all the zeros with ones, minus ones, because that will lead you to a math domain, and then you can deal with substrings and sums, right? And the second technique was the subarray sum is nothing but difference of two elements in the prefix sum array. Third technique was that subarray sum equal to 0 means identical prefix sum, and identical prefix sums can be maintained in a map when you are iterating from left to right, right? Then the fourth technique was, instead of trying to solve the problem of computing all the substrings and then computing their answers, you start with the answer and you see which substrings will contain this answer, right? And the final technique and the fourth and the next technique that we discussed is that instead of dealing with a subarray, start with an fixed one endpoint of that subarray and then see how their contribution varies, right? So when you are varying this x, you see how their contribution varies, and you will realize that some part of this summation is fixed and some part is varying, and that varying part is very simple. It is simply summation of x star. So you just do summation of x star over all of these values, And how can you do that? You can do that by maintaining the prefix sum map, right? So that's it. That's for the problem. Now I have intentionally kept it a bit vague. I did not dive into the implementation details of like what should your x and x star be, but I hope the high level idea is clear. Now if you want to submit this problem, I will link it in the comment section or in the description of YouTube video, and you can submit this problem there to verify whether your reasoning was correct or not. But even if you don't, I hope you understood all the contribution technique ideas that we have discussed. Thank you.